Maybe now it's the time. We're ready. Um, okay. Today we have Jack Davis, and from uh, maybe you need to help
Wo-
me with the pronunciation of the German
Wuppertal.
word, Wuppertal University, and he will tell us about the detection methods with synthetic spectra.
Okay, thank you. Thanks for the invitation again. I am very happy to speak here. So my goal for today is to talk about, well, exactly what's written here in the title. So I want to understand, sorry, I need to, maybe if I'm down there, that works best. How do I make this go away? Ah, perfect. Um, I want to talk about detection methods. So that means I want to understand something like the stable homotopic groups of spheres, and I want to do that by starting with some detection spectrum, some R, whose homotopy groups we know really well. And I want to study sort of the image of this map. So classically, the image of this map is the Hurevich image. It was called the Hurevich image of R, and you can get a lot of information about the sphere spectrum on the left from these homotopy groups and by studying this map. And but what I want to emphasize is that even if you're only interested in the classical stable homotopy groups of spheres, if you can study this map using synthetic methods, so using synthetic spectra, filtered spectra, and stuff like this, you can get much stronger statements. So that's what I'm going to emphasize this whole time. So the talk is roughly broken up into four different parts. I'll start with some low-dimensional examples. So these will be examples that you hopefully find very easy and obvious, but they're going to sort of, I'm going to take the opportunity to lay the groundwork for a lot of the things that come later. So we're going to look at how to prove lots of elements in the stable homotopy groups of spheres are non-zero in very small dimensions where we have lots of different methods. Then I want to talk about how to periodify these examples. So a lot of these low dimensional examples will be eight periodic. And I want to talk about sort of the way to turn low dimensional examples into eight periodic examples in the stable homotopy groups of spheres. This is all so far classic sort of height one work that you can sort of get out of Adam's famous J of X4 paper too. But once we've got all of that behind us, and we'll spend a lot of our time thinking about these first two sections, I want to talk about the height two situation. So how you can apply these techniques to things like topological modular forms and get even more information about the stable homotopy groups of spheres. Um, and then towards the end, I want to talk about, well, I've written here iterations and future ideas, but it's just sort of like, you know, what happens when you go to different heights, when you go to different primes, when you look at motivic spectra or equivariant spectra, like these techniques are very generic, so they apply to a lot of situations. So I want to talk about sort of some future directions with whatever time I have left over. Um, and it's great that Gushwan said that this will be recorded, but I'll also make my notes available too. So don't feel like you have to keep pace with my writing because I'm just going to be scrolling through some things. It might be a bit fast. And the second thing is that all of this comes out of joint work with Christian Carrick, who spoke a few weeks ago at this seminar. And if you want to find precise statements of everything that I talk about here, and if you want to find proofs of them too, you can find that all in joint work with Christian Carrick. So there's a few papers of ours that talk about, start with the height one situation and then talk about the height two situation at various primes. Okay, and feel free to interrupt at any time or post a question in chat. I'll try to keep my eye on the screen. Okay, then let's get started with the low dimensional examples. So this is a very simple example. So let's write, I said I would use my marker so that I would slow me down. Okay, low dimensional examples. So let's write eta for this classical Hopf map. And we'll also write eta for the associated element inside the stable homotopy groups of spheres. Okay, great place to start. So we know that this element in the stable homotopy groups of spheres is non-zero. You can prove this in many different ways. I'll talk about a few later on. But you can also prove it in many classical ways, like by studying cohomology operations on projective spaces. Oh, and in fact, you can also show that the square of this element is also non-zero by using some tricks with Adem relations. look at the end of Hatcher's book. He sort of talks about this in quite a bit of detail. Okay, so there is now a natural third question you could ask yourself, and that is, well, what happens to the third power of eta? I said that we would start with something very simple. Okay, so that's a question. Does eta cubed inside the stable homotopic groups of spheres vanish or not? And maybe you already know the answer. Like I said, well, we're starting slow. So I want to now talk about a bunch of different methods that you could use to prove this. So the first method is number 0, and it is that you could just compute the stable homotopic groups of spheres. Like you could just compute them as much as you need to understand eta cubed, so up to dimension 3, and then you would see that eta cubed is non-zero. And maybe you're doing this with the atom spectral sequence or the Adams-Novikov, but this is really something you can do by hand. Like you can really write down a minimal resolution by hand and have a little table on. You can do it on an A4 sheet of paper. But unfortunately, and I think this technique is really good. I think we should not forget this technique, but it's not very useful for generalizations too. You can't just try to compute all of the stable homotopic groups of spheres to understand all questions of this form, because at some stage these groups just become way too complicated. We only really know what these groups are up to d is around 90, although new computer computations bring us heaps further. But still, it's sort of a finite process. We're probably never going to know all of these groups for each d. Okay, so I want to talk about some other methods of proving that eta cubed is non-zero, which do generalize well. So they admit sort of periodic generalization. And they're all going to use KO as a major ingredient. So KO here being real topological K theory. I'm going to use connective K theory. You can use periodic K theory if you want. It just makes your pictures a little bit bigger sometimes. Okay, so just to remind you what KO looks like, it has this 8 periodic homotopy groups where you have a Z in degrees congruent to 0 and 4 mod 8, and you have an F2 in degrees congruent to 1 and 2 mod 8, and these F2s are themselves generated by eta and eta squared. So in other words, we have a map from the sphere to KO, coming from the fact that KO is a ring spectrum, coming from the fact that you can take the tensor product of real vector bundles, and eta inside pi 1 of the sphere spectrum is sent to this generator, this non-zero element inside pi 1 of KO. And then we have this element alpha generating the thing in degree 4, and everything is repeated 8 periodically. So if you want to, so we sort of have these beta to the k for k greater than or equal to 0, and then we have eta, beta to the k, and etc. For all k greater than or equal to 0. Great. So notice that since eta is non-zero inside the homotopy groups of KO, then in particular, it's non-zero inside the stable homotopy groups of spheres. So this is another way to see that eta is non-zero. And this is also another way to see that eta squared is non-zero, if you didn't like this, this Adams relation suggestion from above. Okay, but notice that pi 3 of KO is 0, so this doesn't immediately give us an answer about the fate of eta cubed. Yeah, so that's what I've written here. So inside KO, eta cubed vanishes, so it doesn't give us any information about what eta cubed does in the sphere. So to actually see how we can use KO to prove that eta cubed doesn't vanish inside the stable homotopy groups of spheres, we're going to be using the Adams-Novikov spectral sequence associated to KO. Yes. So these Adams-Novikov spectral sequences are going to be our sort of our synthetic tool, more or less. So in other words, when I write down the AN of KO, so the Adams-Novikov spectral sequence for KO, I really want to think about it as a synthetic spectrum. So a synthetic spectrum is, well, there is an infinity category of synthetic spectra, and the objects in this infinity category are more or less Adams-Novikov spectral sequences. And this is an infinity category, and it has limits and co-limits. You can take fibers and co-fibers and stuff like this. And it has many remarkable properties. This is the MU synthetic spectra of Piotr Prostrogovsky. But actually, for most of this talk, we don't need to think about synthetic spectra. You can really just think about filtered spectra. So let me just remind you how we think about filtered spectra and how we connect filtered spectra and spectral sequences together. Okay, so here's a definition. So if we have some spectrum X, we can define its Adams-Novikov spectral it's Adams-Novikov spectral sequence in the category of filtered spectra, which is just the pre-sheaf category on the integers mapping to spectra. As well, we take the usual Adams tower for MU, or the MU-based Adams tower for X, and then we apply a kind of décalage functor. So what does this do? Well, if you want to compute the Adams-Novikov spectral sequence for X, this is a standard resolution to use. But the problem is that if you take the homotopy groups of this spectrum, or the bigraded homotopy groups of this cosimplicial spectrum, you don't end up with the E2 page of the Adams-Novikov, but you end up with the E1 page. So we somehow need a mechanism that helps us go from the E1 page to the E2 page, and this is this décalage construction of Deligne. Décalage. Okay. And it's a very explicit functor. It's given by taking level-wise Whitehead towers and then taking a limit in this variable here. Okay, so in particular, I've given you a formula for the Adams-Novikov spectral sequence of a spectrum inside this category of filtered spectra. Great. So how do we think about filtered spectra as spectral sequences? Well, just like we can construct a spectral sequence from a chain complex, we can construct from a filtered chain complex, we can construct a spectral sequence from a filtered spectrum just by taking homotopy groups. So this is this functor here is really similar to the spectral sequence of a filtered complex. So this is how we turn filtered spectra into a spectral sequence. But it will be very useful to actually remember that we started with a filtered spectrum. It'll be very nice to have this sort of extra homotopical data around. It would be more useful to live in the category on the left than the category on the right. And we'll see a really explicit example of this later on. The point is that in the category of filtered spectra, as a pre-sheaf category, it is presentable, it has limits and co-limits, it's symmetric monoidal, it's a very lovely category to work in. Whereas the category of spectral sequences, this one category, is just really terrible. You cannot, it's a very badly behaved one category. You cannot take all the limits and co-limits you want and get the long exact sequences on E2 pages and stuff like this. It's a bit of a horrible category to work in. Okay. So there's one more thing that I want to describe about using filtered spectra, and that is this graded spectrum functor. So this is a functor that goes from filtered spectra to a product of the integers of spectra. So this is what people sometimes call graded spectra. And what this functor is it's taking your filtered spectra, and it's just taking the sort of pairwise quotients. So if you imagine your filtered spectra as an object as sort of this chain of spectra, then if you just take all of the quotients, so you take this guy and the map between them, and then you take the associated co-fiber, then you end up with uh, this collection of you end up with this graded spectrum. And this functor is constructed in such a way that if you take the homotopy groups of the graded of the, if you take, let me highlight this. If you take the sth homotopy group of the fth graded part of, say, the Adams-Novikov spectral sequence for some x, you really end up with the E2 page of the classical Adams-Novikov spectral sequence. Okay. I'm not assuming that everyone is familiar with this sort of homotopical perspective on spectral sequences. If you want to think about everything just as a spectral sequence, you're not going to go too far astray. But at some stage, I'm going to be taking fibers and cofibers, and it's much better to work in this category once I start taking these fibers and cofibers. But feel free to ask questions if anything comes up. And another thing is that a collaborator of mine, Sven van Nijteveld, has a great paper on the archive recently, last month, that's called Filtered Spectra and Synthetic Spectra, or something like this. And it's a really great introduction to using filtered spectra and synthetic spectra as homotopical objects that capture spectral sequences. I think that's a great reference. There's also some great references, including Alice Hedenlund's thesis and a new paper of Ben Antiou. I never learned French. I can never spell Ben Antiou's name. I don't know. There is some collection of vowels at the end. My apologies, Ben. Okay. So, let's get back to the situation we want to talk about. We want to talk about the Adams spectral sequence, or the Adams-Novikov spectral sequence for KO. And that has the following familiar picture, hopefully. Some of you might recognize this as looking very similar to the homotopy fixed point spectral sequence for the conjugation action on Ku, and you would be right. It's basically exactly the same up to some connective cover. Okay, so this is what, and in fact, that's one really convenient way of computing the E2 page of this spectral sequence using this homotopy fixed point perspective. Okay, so this is what the E2 page looks like. And let's just compute all the differentials quickly. So we know that, let me just tell you some facts. So we know that eta appears in the homotopy groups of KO, so it has to appear in this element here, because we're reading the homotopy groups of KO are appearing as these columns here. So we know that this element has to be eta. This element is eta squared. And so this element here, which would represent eta cubed, it has to somehow die in the spectral sequence. And the only way for it to die is, well, there's nothing up here for a differential based on eta cubed to hit. And, well, eta cubed is a permanent cycle because it's a product of permanent cycles. So it has to be hit by a differential like this. And in fact, the Leibniz rule then gives us differentials all the way up this eta tower. And moreover, we can now look and notice that this does a really good job of approximating the homotopy groups of KO, because we have a Z in degree 0, two F2s in degree 1 and 2. The kernel of a map from Z to F2 is still Z, so we still have a Z in degree 4. And in degree 5, 6, and 7, everything has vanished, because everything up here is either the source or a target of a differential. Then we come to degree 8. So we know that a generator here is given by this beta class. And, well, there's nothing up here for beta to hit. So that means that beta is a permanent cycle. And that means that by the Leibniz rule, we can... what color do I want to use? Let's use this color. By the Leibniz rule, I can propagate this differential using multiplication by beta to fill out the whole spectral sequence. And in fact, this one key D3 differential generates the whole spectral sequence. Okay. I also want to, for future reference, I want to give a name to this class on the E2 page. So the class here, which supports this D3 differential, which kills eta cubed, I'm going to call U squared. And it's called U squared because it comes from the periodicity generator of Ku. Okay, so I told you that we want to think about eta cubed being non-zero, and then I went on this tangent about the Adams-Novikov spectral sequence for Ko. So how can we now use this Adams-Novikov spectral sequence to prove that eta cubed is non-zero in the stable homotopy groups of spheres? Well, as I mentioned, we can't just use the homotopy groups of Ko because, well, eta dies in these homotopy groups, but notice that eta cubed is non-zero if we consider it as an element inside this map between E2 pages of the Adams-Novikov spectral sequence. So in particular, I want to say that this class eta actually lies in the synthetic Hurevich image of Ko. So it's a class that, although it's not detected in the actual homotopy groups of Ko, it is detected in the Adams-Novikov spectral sequence. And I just want to use the language of synthetic Hurevich image to state this fact. Oh, excuse me. Okay, so now I want to talk about at least three different ways to show that eta cubed is non-zero in pi3 of the sphere, just using this Adams-Novikov spectral sequence for Ko. Okay, so the first method is I'm going to call the filtration of source method. And I'm gonna quickly read through the argument, and then I'm going to go back to the spectral sequence because I think it's much easier to see the argument than hear it. So the point is that there is a D3 which kills eta cubed in the Adams-Novikov for Ko. And the source of this D3 has filtration 0. So it really, this differential has base on the 0 line of this Adams-Novikov spectral sequence. So we can ask ourselves, does this D3 differential come from the sphere spectrum? Well, no. And the reason why this differential can't come from the sphere spectrum is just because the 0 line of the Adams-Novikov spectral sequence for the sphere is 0. This is one of the first things that one would prove when you start studying the atom spectral sequence in general. And it's essentially true because the homotopy groups of BP or MU are torsion-free. So in particular, this D3 for the this D3 that killed eta cubed in the Adams-Novikov for Ko cannot come from the Adams-Novikov for the sphere. So then the only way that eta cubed could die in the Adams-Novikov spectral sequence for the sphere is if it's maybe killed by an even bigger differential. Thank you, David. But it can't be killed by a bigger differential because then that bigger differential would have source in even lower filtration, and that's just absurd. So let me go back to the picture and show you that. So I'm looking at this differential here, and I'm saying that the source of this differential is concentrated on this 0 line, and this 0 line, the zero filtration 0 of the atom spectral sequence of the sphere is 0 in positive degrees. So this differential couldn't come from the sphere. Okay, great. And then it's a few more steps by a degree argument to say that nothing else could hit eta cubed, hence eta cubed has to be non-zero in the sphere. Okay, so that's the first argument. And here is sort of the moral takeaway from this argument. It says that if you're working with the Adams-Novikov spectral sequence of some detection spectrum, and you have some differential in this Adams-Novikov spectral sequence for R, which hits some class X, and say that X lies in the synthetic Hurevich image of R, and the source of this differential is in low filtration, then this differential could not come from the sphere. So it's sort of, yeah, this is just the situation. And we'll see more examples of that later. Okay, so there are two more techniques that I want to go through quickly now. In fact, the first one I'm going to skip for now, and I'll talk about it at the end if I have time. So there is a similar sort of Toda bracket argument you can make here, where you essentially say something like, well, for those of you who are familiar with Toda brackets, you essentially say, if eta cubed was 0 in the sphere, then a Toda bracket that looks like this would necessarily be non-empty in the sphere. It would be well-defined. And then you can use the linearity of Toda brackets to show that the map from pi 4 of the sphere to pi 4 of KO has to be non-zero, which is absurd because pi 4 of KO is torsion free and pi 4 of the sphere is torsion. Um, yeah.
Uh, yeah,
Mhm.
can I ask a very annoying question? Like
Yeah,
for
please.
the how to show the total bracket is non-empty. Oh, sorry, I agree with non-empty, but it's non-zero, right? Because zero is can it can
I
contain
totally agree.
zero.
I
Yeah.
totally agree. So what you do is you show that its image in KO doesn't contain zero.
Oh, I see. Cool.
Yep. So you essentially
Thanks.
compute this Toda bracket in KO, and the reason why I mention it now is because you make this computation using the Adams-Novikov.
Oh yeah, I saw you write it. It's non-zero in pi 4KO.
Yep.
Thanks.
Yep. Good question. Yeah, I'll mention this argument in a bit more detail at the end if we have time. Um, the third method I want to mention is somehow more powerful than the other two methods, and I want to call it, I don't know, I gave it a silly alliterative name, like deleting differentials. So you need a few more tools to apply this technique, but essentially, uh, the only extra tool that we need in this situation are Adams operations. So we're going to use the psi3 Adams operation on KO. So let's assume that we're working in the two complete world now, so that we have this Adams operation. Um, yeah, sorry, so that we have this Adams operation on KO. Then we can compute what these Adams operations. Let me just maybe write down the syntax for this Adams operation. So it's a map of spectra, a map of ring spectra from KO to KO. And implicitly, we're working with 3 inverted now. Now, a classical computation, so in other words, using vector bundles or using some formal homotopy theory, you can compute what these Adams operations do on every element inside the homotopy groups of KO. It's reasonably straightforward. You see that it acts trivially on eta by multiplication by 3 to some power on these torsion-free elements. But notice that by functoriality of the Adams-Novikov spectral sequence, psi3 also acts on the Adams-Novikov spectral sequence for KO. Okay, and now we're going to just stare at this differential, this D3, this key D3 differential that I'm going to keep coming back to. We're going to stare at this and notice something. The key observation is that this differential is, of course, defined by its source and its target. And notice that the Adams operations act trivially on the target, but that the Adams operations act non-trivially on the source. So when I write an equation like this, I'm of course meaning it as it has to be taking place inside the E2 page of the Adams-Novikov spectral sequence for KO. And computing the Adams operations on the E2 page essentially follows by this or the Adams operations on KU. So notice then that I can do the following trick using this little observation. Maybe I'll highlight that observation as well. And the trick is as follows. If we work in filtered spectra and I define something that I'll just call F as the fiber of this Adams operation -1 acting on the Adams-Novikov spectral sequence for KO, this is some kind of modified Adams-Novikov spectral sequence for this fiber taken in classical spectra, which sometimes people call this. It's very similar to the image of J spectrum that people study. Then, well, we have a filtered spectrum here. So in particular, I have a spectral sequence. In particular, I have an E2 page of this spectral sequence, and I can compute this E2 page incredibly explicitly because I know the E2 page of the Adams-Novikov for KO. I know how to compute the Adams operations on this E2 page. And since this functor, where is it? Since this associated graded functor is exact, it means that the E2 page that I compute for F can be computed by a long exact sequence. Yes. So in particular, yeah, so you can compute the E2 page of F just by a long exact sequence. And notice that this little computation that I made above tells us that we have eta cubed here, and it's sent to, maybe I should write that so it doesn't disappear. We have eta cubed here. It's sent to eta cubed minus eta cubed is equal to 0 here. So it admits a lift to f. Whereas this element u squared, it's sent to 3 squared u squared minus u squared, so 8 times u squared is non-zero, so it doesn't admit a lift. So in other words, the target of this differential lifts to f, but the source of the differential doesn't lift to f. Like I said, I think someone can explain spectral sequences to you all day, and it can be hard to pass what they're actually saying. I find it much easier if they have a picture. So I have a picture here. So in this picture, I have the Adams Novikov for KO in blue, and the target Adams Novikov spectral sequence for KO in red. And so because I have a fiber sequence, I of course have this boundary term, which is, again, going from the red thing to F. So in other words, everything that's blue here is something that's in the kernel of this map that I'm lifting, and everything that's in red is something that's in the co-kernel of this map and the image of this co-kernel through the boundary map. It's a dimension shifting boundary map, and that's why we see a lot of the Adams-Novikov spectral sequence for KO appear here. And then we see a shift of that where you shift to the left by 1 and up by 1 in red. And you can see that there used to be a class here, a u squared, that used to support a differential. But since u squared is not in the kernel of this map, it doesn't lift to f. And so the source of this differential disappears. And so eta cubed survives this spectral sequence. So, yeah. And in particular, oh, sorry, was there a question?
No, I was hesitating. So does it take the fiber of a filtered objects? Is it the same as level-wise take fiber and form a filter objects?
Yep. Yep.
Okay, thanks.
Yeah, no worries. And I mean, whatever filtered object you have, I claim that we don't even really need much information about that. We just need the fact that we have we can compute the E2 page, so we can compute the associated graded by taking fibers and cofibers on the E2 page. And all the differentials in the spectral sequence, they all just come from either the blue side or the red side. So notice that there are no differentials. I'll zoom in a little bit. Notice that there are no differentials that go from red to blue or from blue to red. They all stay within their own color, which is telling you that all the blue ones are coming from here and all of the red ones are coming from here. Okay, great. Oh. So in particular, we have some E-infinity page of the spectral sequence that we computed, and it looks very neat. It looks like this. Okay, so in particular, we can see that eta cubed has to be non-zero inside pi 3 of whatever this fiber happens to be in spectra, which again is something that people call J, or is very closely related to what people call J. So if eta cubed is non-zero here, then in particular, it's non-zero in the sphere. Okay. I like this deleting differentials technique, and not just because it's fun to say. So I want to make 2 remarks before I move on to the more general applications. The first one is that this spectral sequence is easy because we have the Adams-Novikov for KO, and to compute this spectral sequence, all we need to do is take fibers and cofibers and move all the differentials that we can from the blue to this spectral sequence, from the red to this spectral sequence. And in the end, it collapses on the E4 page. So this spectral sequence was very easy to compute, but notice, the Adams-Novikov spectral sequence for this guy is in general not well understood. So notice that I haven't taken the Adams-Novikov spectral sequence for this spectrum. I don't even really care what it is. I'm studying this spectrum by taking the fiber in filtered spectra and studying the associated spectral sequence. Also notice that this deleting differentials technique is it's actually stronger than these first two techniques. So this filtration technique and the um, Toda bracket technique that I didn't give in detail. And it's stronger because it doesn't just say that eta cubed is non-zero, but it gives you a new detection spectrum. It gives you a new place where eta cubed is non-zero. So in particular, now that we have this spectrum and this spectral sequence, we can now apply the same sort of techniques. We can now apply these methods 1 through 3 again to this fiber and try to get even more information. So the nice thing about the third technique is that it's somewhat iterative. You can sort of apply it as many times as you need until things get too complicated or until the problem is solved. Okay. I knew that first part would take
I have a question.
Yep.
Why is it called deleting differentials?
Yeah, so me and Christian call it that because we really sort of view it as like we're in this situation like this, and we did have this differential, and we've somehow deleted it by finding an endomorphism of this spectral sequence where the target is fixed, but the source is not fixed. So yeah, I think that's why I call it that. Cool. Were there any other questions at all? Okay. Okay. So yes. Okay. So at the beginning, I said that you could. I mean, I've talked a lot now about eta cubes being non-zero, but I also said that that's pretty obvious that we could just compute the atom spectral sequence or the Adams-Novikov spectral sequence, and that would be pretty clear. But what's very useful about these techniques, so technique 1 through 3, is that they periodify in a very nice way. So I want to just quickly now talk about how to set up this periodic 3 in this periodic how to set up this periodic theory at height 1 and what sort of results you get. So so the first fact is we want to periodify this fact that eta cubed is non-zero, and to do that we use a V1 self-map on this mod 2 Moore spectrum. So one way to construct this self-map, so in other words, it's going to be a map like this. One way to construct this map is to take a class like 8 times sigma. Notice that since we know that 16 times sigma is 0, at least 2 locally, then 8 times sigma lies in the kernel of this multiplication by 2 map, so it lifts along the boundary to an element in pi 8 of the mod 2 Moore spectrum. And if I have an element inside pi 8 of the mod 2 Moore spectrum, so let's call it V1 for twiddle, going to the mod 2 Moore spectrum, to define this self-map, all I need to do is show that it factors through this inclusion into the bottom cell. And that is clear because one just shows that precomposition with 2 is 0. And then one gets this factorization. Okay. And so once you have this self-map, you can define periodic classes as follows. So we get what's called Adams' mu family. And their elements here, which are defined as follows, they're all of degree 1 plus 8d. And first you apply the projection to the mod 2 Moore. Then you apply a default iteration of this self-map. And then you apply this boundary map of the mod 2 Moore spectrum back to the sphere. And this produces a whole bunch of classes inside a whole bunch of classes which we call mu 1 plus 8d inside the stable homotopy groups of spheres. Okay, so we've produced all these classes, and it's actually a challenge at first to prove that they are non-zero, because I've just constructed a bunch of elements using a bunch of maps, and maybe they cancel out or something at some stage. So the claim that proves that they are non-zero, well, a claim that proves that they are non-zero is to show that these classes are actually mapped to eta times the periodicity class inside the homotopy groups of KO. So to show that all of these classes here are sent to eta times b to the d. inside pi 1 plus 8d of KO. In particular, that's also going to tell you that eta times mu 1 plus 8d is also non-zero in the sphere because it's also mapped to a non-zero element inside KO. And now you might get a feel for what I'm going to ask next. I'm going to say, well, what about something like eta squared times mu 1 plus 8d inside the stable homotopy groups of spheres? And if you just copy the arguments, I think that if you're really interested in this, I think this is a great time to do something on a piece of paper at home, is to try to copy the arguments 1 through 3 to prove that this guy is non-zero inside the stable homotopy groups of spheres, using the Adams-Novikov for KO and using this filtered spectrum F. Okay. Yeah, so this is one way in which you can periodify these sorts of statements. I have a little bit more written here, but I think I want to skip that for now and move on to the height 2 situation. Are there any questions about this periodification technique that I just dumped on everyone? Yeah. Okay, then, oops. I won't be able to get home if I lose my keys. Yes, okay, then let's go on to height 2 generalizations. So everything that I just explained now to do with eta, to do with this mu family, to do with KO, fits into chromatic homotopy theory, into what chromatic homotopy theory would describe as sort of height 1 phenomena. So phenomena that are sort of originated in the filtration 1 of the Adams-Novikov spectral sequence for the sphere. But as height 1 probably suggests, there are generalizations of this, and the generalization of KO at height 1 to height 2 is TMF. So this is Hopkins' E infinity ring of topological modular forms. So there is a beautiful history of how it was discovered and all the different ways in which it's used. But at the moment, for the purpose of this talk, I just want you to think about it. It's as a detection spectrum. So it is something whose homotopy groups we really understand, which has a really interesting Adams-Novikov spectral sequence, and whose Adams-Novikov spectral sequence we're going to use to check some non-vanishing of elements in the stable homotopy groups of spheres. So let me just give you an example of what the Adams-Novikov for TMF looks like. Sort of in very low degrees, it looks very much like KO. It has the same sort of pattern. You have eta, eta squared, eta cubed. In fact, if you had access to TMF, you wouldn't need to prove that eta cubed is non-zero using the techniques. You could just check that it's non-zero in TMF by hand. But it doesn't just have this K. Oh, yes, and I guess it also has this like mu9, eta mu9, and stuff like this. Mu17, eta mu17. So it has all of this height 1 information, but now it has a whole bunch of new information too. It has new, so the second Hopf element, and it has a whole bunch of interesting height 2 classes like nu squared, a class which we call epsilon, a class in degree 14 that we call kappa, and everyone's favorite height 2 element, kappa bar. So these are all just like the amazing thing about the Adams-Novikov for TMF is that for KO, we somehow only had a very small collection of things to work with, but for TMF, we all of a sudden have all of this different information to work with and all of the interrelations between all of them. So it's going to be a lot of fun to really figure out what's going on. Okay, so let me see, let's have a look at the kind of arguments that we can make in the Adams-Novikov spectral sequence of TMF using these methods 1 through 3 that I mentioned above. So the filtration argument, the total bracket argument, and the deleting differentials argument. Okay, so to do that, I went a little bit further along in the spectral sequence because we need to see a little bit more information. So maybe okay. So for example, we have this class kappa bar in degree 20. Well, in the 20 stem in filtration 4. And you can multiply this class kappa bar and you get this class nu kappa bar here. But nu kappa bar is 0 in TMF because it's hit by this differential. But now run all of the same arguments that I said before, notice that this differential hits a class inside the synthetic Hurewicz image of TMF. I mean, nu times kappa bar lies in the image of the E2 page of the Adams-Novikov spectral sequence of the sphere, because that's true for kappa bar and because that's true for nu. I'm ignoring the filtration jump for kappa bar here, and I will for the rest of the talk. So I have an element that lies in the synthetic Hurewicz image of TMF, and I have a differential whose source has filtration 0. So this differential can't come from the sphere. And then a degree check tells you that actually this element has to be non-zero in the sphere. Fantastic. You can also make this argument for eta cubed times kappa bar here, because there is a longer D7 differential here. So here we have a D5, and here we have a D7. Okay, but notice that we can actually continue this sort of argument, because we also have nu times this D5 differential. It's now hitting nu squared.
This is a special show only for people here, not for people online. Watch the record.
Yeah. Okay, I think I just heard that it came back.
Okay.
Good. Yes, so notice that unlike the KO situation, when we could only apply this argument for one differential, that we can apply it not just for this D5 and this D7, but we can also apply it to nu times this D7. Now, the filtration of the source argument is not immediately going to work here, because this differential now has source 1. And maybe something in filtration 1 in the atom spectral sequence of the sphere might actually hit this class here, and maybe this D5 comes from the sphere. But we also understand the filtration 1 information in the Adams-Novikov spectral sequence for the sphere, so you can also use argument 1. So let's say that argument 1 shows squared times kappa bar is also non-zero in the sphere. But there is also, and you can also have fun at home. You can try to prove that nu times kappa bar is non-zero using the total bracket argument. That's good fun. But you can also use a version of argument 3 for TMF. But you don't want to use Adams operations on TMF. You want to use a slightly different tool. So I've actually written down some of these arguments here already. So yeah, if we want to show that this guy is 0, we can use this filtration argument. But if we want to show that nu squared times kappa bar is non-zero, we can either use the filtration argument, or we can use a deleting differentials argument by mapping TMF to TMF with some level structure. So TMF with some level structure always comes equipped with a canonical map, which I've called here can. And TMF with level structure also has an interesting involution called W, which is the Atkin-Lerner involution. Can you not argue that the differential from 7.1 is propagated from this, which no longer exists since you don't know? No, you can't quite use this because so I think what David is trying to get at is, can you say something like this D5 can't come from the sphere because this D5 doesn't come from the sphere? But you can't argue that because, and we can see a counterexample in KO, for example. So this D3 doesn't come from the sphere, but eta times it actually does. So yeah, unfortunately, this argument doesn't work. You have to be very careful with these sorts of things. No worries. Yes. Okay. Let me just mention while we're here that even though this element is non-zero in the sphere, and even though this element is non-zero in the sphere, so nu times kappa and nu squared times kappa, it actually turns out that nu cubed times kappa is 0 in the sphere. And it's interesting to see which parts of the arguments 1 through 3 do not apply to this D5, which did apply to this D5 and this D5. One has to be very careful in this world because, but I think TMF is a great place to experiment with these ideas because lots of things are true and also lots of things are not true. Okay. So yes, so this gives you a lot of non-vanishing of a lot of these sorts of classes. Not this one. And this happens all over. So you could also look at something like kappa bar squared times epsilon. This is a class over here, and this is hit by, is that a D9? And you can delete this D9 again using this Atkin-Lehner involution. And you can also periodify a bunch of these results. So at height 1, we had this eightfold periodicity, this V1 to the 4, but Behrens, Hill, Hopkins, Mohold proved that at height 2, you actually have a V2 to the 32 periodicity. So this gives 144-fold periodicity. And by combining these periodicity arguments, together with techniques 1 through 3, with the Adams-Novikov spectral sequence for TMF, Christian Carrick and I could prove something like this. So I'll just read it out loud. The above techniques applied to the Adams-Novikov spectral sequence for TMF produce 125 non-zero periodic families in the stable homotopy groups of spheres, which all vanish in the homotopy groups of TMF. And I like this number because it's big, but it's somehow not super important. I mean, if it was 20 or 600, I would still write the theorem down in exactly the same way. It's just the number that we found when we were checking the spectral sequence page by page very carefully, trying to enumerate things correctly. And this is great because not only does it help me understand how TMF influences the stable homotopy groups of spheres, or how you can use TMF to understand the stable homotopy groups of spheres, but it also tells you some very classical things. So for example, you can use Kaveh-Milner's paper on the groups of stable homotopy spheres to show that there are exotic spheres of dimension D for all dimensions D congruent to these three numbers. So we know that there are many more even numbers where there are exotic spheres in all dimensions congruent to that mod 192. And we just added a few more using these new families. Okay. And just to give you an outline of the proof, it's really as simple as everything that I've said so far. You need to first compute the synthetic, well, some of the synthetic Hurevich image of TMF, which often comes from the classical Hurevich image. And then you need to run through all of these sorts of filtration arguments and deleting differential arguments and so on. Let me mention a really subtle point, because this is one point that makes the paper much harder, is that the synthetic Hurevich image of TMF is actually very complicated, and we don't know what it is yet. So here's an example of an element here. So it's not the generator here, it's the outer circle. It's an element that I usually call something like 2 nu kappa delta. And we show that this element is in the synthetic Hurevich image of TMF, but notice that it's not in the classical Hurevich image of TMF, and it's also indecomposable. So it's very easy to prove that an element like epsilon kappa bar squared lies in the synthetic Hurevich image because it's a product of two things that lie in the classic Hurevich image, and this information usually implies that the product lies in the synthetic Hurevich image, whereas this guy doesn't lie in the classical Hurevich image. So, and it is indecomposable. So there were a few elements like this that me and Christian had to work really hard to try to produce synthetic lifts of. Yeah, I wanted to mention that because it was hard work. Okay. Okay. Are there any questions about that so far? I'll mention a few more things quickly before I stop. Okay. Yes. So you hopefully have a lot of natural questions. So everything that I talked about with this theorem and this corollary together with Christian Carrick is all stuff at the prime 2. So we've implicitly 2 completed or 2 localized, and so it's all 2 local information. So one can also ask about 3 local information. So here is what the Adams-Novikov spectral sequence for TMF looks like at the prime 3, and notice that it's much smaller and neater. And so me and Christian could actually work pretty well with this. We could actually compute all of the classical Hurevich image of, we could compute all of the synthetic Hurevich image of TMF, as well as the classical and synthetic Hurevich image of the fiber of Adams operations on TMF. And it was at this moment that I realized how powerful this step 3 was. The fact that you can iterate it. The fact that we can use the Adams-Novikov spectral sequence of TMF to make detection arguments by deleting differentials, but then we can also compute the Adams-Novikov spectral sequence for this spectrum, or a modified Adams-Novikov spectral sequence, and then try to run the same arguments again. Try to run this source, this filtration on the source argument, try to run this deleting differentials argument. And so here is what happens when you run that. So again, the blue stuff is the Adams-Novikov spectral sequence for TMF, roughly. And the red stuff is the Adams-Novikov spectral sequence for TMF, but shifted. So again, I used similar color scheme as before. The blue stuff is coming from this part of the fiber, and the red stuff is coming from the image of the boundary map. But since we can compute this whole spectral sequence, you can now run all of these arguments. You can say, here is a differential, for example, that's killing beta squared times beta 2, whatever that element happens to be. But this differential has source in filtration 1. And I understand all of the filtration 1, well, not just me, a lot of people understand the filtration 1 Adams-Novikov spectral sequence for the sphere at the prime 3. And so this differential is gone. This guy is a permanent cycle, a non-zero element in stable homotopy groups of spheres. You can make the argument with this differential, this D9 that's killing beta 1 to the 5. And you can also run these arguments periodically, of course. That's one of the takeaways of these techniques. So one thing that I just wanted to mention quickly before I finish is that recently I was thinking about these sorts of detection statements using exactly this spectral sequence, and you can prove a lot of non-vanishing statements, so a lot of detection statements using these sorts of deleting differentials techniques and filtration techniques, but you can also go one step further, and you can show that certain differentials periodify. So certain differentials, like for example, I'm not going to find one if I look for it. I know this one, for example. This differential here, which is killing alpha 1, beta 1 cubed, you can show that this differential itself periodifies. So that tells you that not only is alpha 1, beta 1 cubed 0 in the sphere because it's hit by a differential, but you can, by periodifying the differential, you also see that alpha 1, beta 1 cubed and the whole periodic family generated by that is also 0. So for example, before the sort of statements that the theorem that I wrote down before, joint with Christian, was saying that given some conditions, we can show certain things don't vanish. But by periodifying differentials, you can also show the converse. So you can also show that if, well, for example, as stated here, if a certain power of an element is too big, then actually this element in the stable homotopy groups of spheres is 0, because the thing that witnesses this element dying, this differential has been periodified. Okay, that's sort of roughly where I want to leave it with in terms of techniques and theorems and statements and stuff. But just because it would be insulting not to mention it, I just want to say that I've been talking about deleting differentials by taking fibers. But of course, fibers are just uh, limits of one truncation of a cosimplicial diagram. So it's like an equalizer. And but of course, cosimplicial diagrams are much bigger than this. They don't just have yeah, it's not just that you have two maps here, but you could also have three and then four going up, not to mention the other maps going down. And by taking bigger diagrams and taking bigger limits, you can get even more refined information. So Mark Behrens has had this idea for more than 20 years now of looking at the limit of this spectrum. And there's no reason why one cannot just run the same sort of synthetic methods here. The only obstruction is difficulty. Uh, there's just more work to do, and computing these maps, computing this map and this map is just difficult. I'm hoping that we can figure something out soon. Anyway, thank you for listening, and thanks for the invitation again.
Oh, okay. Thanks for thank Jack for the great talk. And then we can stop the recording, and everyone can feel free to ask more questions.